Hi, this is a presentation of a case study that we've carried out at 1 Canada Square, which is the main tower at Canary Wharf. We installed a 2.5-inch pressure independent control valve on an air handling unit, together with a variety of sensors and data collection equipment to monitor the performance of the valve and the associated air handling unit. We were also able to compare the performance of the air handling unit with a pressure independent control valve fitted to the same air handling unit with a conventional 2-port modulating valve fitted. This presentation shows what we found and draws some conclusions from the data. This is the Frese OPTIMA pressure independent control valve, which is produced in ductile iron with PN16 or PN25 flanges in 2-inch through to 6-inch. It's shown here together with the actuator that is mounted and can give a variety of signals, including 0 to 10 volts and 4 to 20 milliamps. We have both a low pressure and a high pressure version of the valve. The low pressure has a minimum startup of 35 kPa and a maximum pressure rating of 600 kPa. And as can be seen on the slide, from flow settings from 4.4 litres per second maximum on a DN50 to around 44 litres per second on a DN150. There are two main applications for the flanged pressure independent control valve. Firstly, controlling the flow and through an air handling unit. The second key application is mounted on the primary side of a plate heat exchanger, where the valve modulates open and closed under the control of the supply temperature on the secondary side of the plate heat exchanger. So the valve itself, if we take a look at the internals, operates in a way such that the water flows from upstream and enters the bottom of the valve. The upstream pressure then is transmitted through the stem and up above a diaphragm and piston. However, the water now flows in through the inlet of the valve, which is set to the maximum design flow and regulated as the actuator strokes the valve up and down, and some pressure is lost as it enters the valve. The pressure acts upwards on an area, creating a force upwards, which, due to the loss of pressure as the water flows into the valve, is slightly less than the pressure exerted downwards, and consequently an additional spring is included to enable a balance of forces. That balanced force will set the position of the outlet of the valve, which means as the water flows through the outlet and onwards and downstream, the remainder of the additional pressure is now lost, and therefore the pressure difference between upstream and downstream can vary, but the pressure difference between the upstream and the internal to the valve remains constant critically across the controlled element of the valve. This graph shows the relationship between flow and differential pressure. So it can be seen that from the startup pressure, typically 35 kPa, all the way up to the maximum pressure of 600 kPa, once the flow is set at its maximum or somewhere below that, the flow will remain constant irrespective of pressure fluctuations in the pipework, and indeed can only be varied then by the changing actuator position. Because a typical heat exchanger, such as an air handling unit, generally has an equal percentage relationship between flow and power output, as can be seen in the top left hand graph here, it is necessary that the valve and the actuator combination also have an equal percentage characteristic, but this time in the opposite direction. The graph on the bottom left of the slide shows that when the power output and flow characteristics are combined, the result is a proportional relationship between valve lift or feedback signal from the temperature sensor and power output from the coil, leading to proportional control of the temperature. However, the fourth factor is also important. We expect from the theory to have a proportional relationship between valve lift and power output. However, this is affected by the authority of the valve. Convention says we design typically for between 0.25 and 0.5 authority, which, whilst not proportional, is not bad. However, the lower the authority of the valve, the more of a quick opening style valve it becomes, and less control is exerted by the control valve, very often leading to hunting and unstable temperature control. So clearly, choosing a high authority for a control valve is very important. The authority of a two-port control valve is the ratio between the pressure drop across the valve in the fully open position at design flow relative to the maximum pressure drop across the valve in its fully closed position. As we can see from the diagram and the graph, if we are able to size the kV of the control valve very low, then the authority could approach 1. But of course, this means a small valve with very high resistance. If we allow the authority to drop, then this reduces the resistance, but unfortunately the equal percentage control characteristic that we aim for is now no longer achievable. The OPTIMA valve is actually linear, but when we install the actuator that is pre-programmed with an equal percentage characteristic, the combined characteristic of the control valve is equal percent. When this equal percentage control valve, which is always this shape due to the authority of 1, is combined with the equal percentage but opposite characteristic of the output from the cooling or heating coil, then irrespective of the exact shape, which is affected by delta T and whether you're on heating or cooling service, these two characteristics to combine to provide the proportional relationship for the control system as a whole. We installed the pressure independent control valve in the main tower at Canary Wharf in London and installed a variety of pressure, temperature and flow sensors to be able to record the performance of the valve relative to a conventional two-port valve. The 2.5-inch valve was set for a design flow of 5.1 litres per second. With the design flow set at 5.1 litres per second, when the control signal from the actuator was received and the valve fully opened, the flow always returns to 5.1 litres per second. When the control signal is below 10 volts, the actuator changes position and modulates the flow due to the equal percentage control characteristic until tight closure when the stem is fully closed. We installed the pressure independent control valve on an air handling unit supplying cooling to level 6 of 1 Canada Square, also known as DS7. The chilled water system consists of 6 staged chillers and circulating pumps, and the particular segment or circuit that we are interested in is the lower floors chilled water secondary system. The system is designed in such a way that there are two risers that stretch from the lower floors up to floor 27. Then there is a hydraulic brake on floor 28, and the remaining floors are on a different circuit from 28 to floor 50. We're concerned with level 6, where we installed the pressure independent control valve on the south riser air handling unit and monitored performance, whilst we also monitored performance of the conventional 2-port modulating valve on level 6 air handling unit on the north riser. Of course, there could be some different occupancy loads on floor 6 and certainly different solar gains due to the orientation of the building. Therefore, after 2 weeks, we exchanged places of the two valves and recorded data for a further 2 weeks in order that we could average out the month's data and negate some of the variables mentioned. The pipework system has been installed a little over 20 years and is coming up to its full 20-year refit. So we can see that the conventional 2-port modulating valve is somewhat rusted. However, we will see in a little while it's working fairly well in difficult conditions. This photograph shows the OPTIMA pressure independent control valve having replaced the conventional valve. You can also see a variety of pressure, temperature and flow sensors installed in order that we can record the performance of the valve and air handling unit. These two graphs represent the temperature of the supply and return water and supply and return air, together with the outside air temperature. The left hand graph, we can see that the incoming air onto the air handling unit on the south riser is lower than the incoming air onto the air handling unit on the north riser. This of course means that the valve on the north riser needs to allow more flow, as it's having to work harder to reduce the outlet off-coil air temperature down to the set point. The set point for both north and south is 11 degrees. It should also be noted that the dark blue line represents the outside air temperature, and as the data was collected on the same day, obviously the outside air temperature was identical in both the south and the north riser. After 2 weeks, we picked up the pressure independent control valve and moved it from the south air handling unit into the north air handling unit, and took the conventional valve from the north and installed it on the south air handling unit, and once again recorded the temperature performance. We can note from these two graphs that the delta T of the water is much higher on the air handling unit installed with the pressure independent control valve than it is on the air handling unit installed with the conventional control valve. We can also note that whilst both set point temperatures are maintained fairly well, there are less oscillations, and the amplitude of the oscillations are less on the north air handling unit, which has the pressure independent control valve installed on it. The next graph compares the same data collected on the south air handling unit, but on different days, when fitted firstly with a conventional valve and secondly with a pressure independent control valve. It can be seen here also that the water delta T, the difference between the supply temperature and return temperature, is higher when a pressure independent control valve is fitted to the same air handling unit with a conventional two-port modulating valve. We also collected data of the pressure drop across the control valve, which is the dark blue line and can be read against the left-hand y-axis. We can see that this varied between around 200 and 250 kPa on this particular day. However, we also can see that on the light blue line, which is the flow rate through the valves and can be read across the right hand y-axis, that when the system switched on at 7 o'clock in the morning, and of course the air had to be cooled quickly down from a higher temperature, that the flow through the pressure independent control valve spiked up to around 2.5 litres per second, but was still regulated. However, it should be noted that the spiked flow through the air handling unit and the conventional modulating valve was much higher, in excess of 7 litres per second, relative of course to a design flow of 5.1 litres per second. This will certainly lead to a time lag before the higher coils are reduced down to set point temperature. Once again, after 2 weeks, we reversed the position of the pressure independent control valve and the conventional two-port modulating valve. Here we can see the valves both regulated the flow fairly well during an anomaly when the pressure across the valves dropped for a period from 270 kPa down to around 140 kPa. Of course, in the right hand pressure independent control valve, this was achieved through the differential pressure controller operating, and on the left hand two-port modulating valve we can see the stem position increase from around 10% open to around 20% open to maintain a fairly stable flow, but through the changed stem position of the valve. We can see that the stem position of the pressure independent control valve is far more in the central range, and is shown here on this graph as a percentage against the left hand y-axis. The flow is both more stable in the pressure independent control valve and has far fewer oscillations when compared with the flow through the conventional two-port modulating valve. If we show the flow through the pressure independent control valve on the south air handling unit compared to the same air handling unit on a different day but with similar outside temperatures when fitted with a conventional valve, it is noted that the flow through the pressure independent control valve is significantly lower and more stable than the flow through the two-port modulating valve. Whilst we know the authority of the pressure independent control valve will be 1, we can use the data collected and the kV of the DN50 valve to calculate the authority. As we can see, the authority of the conventional two-port modulating valve is less than 0.1, and explains why the valve has to close 90% to absorb the pressure, and explains the frequency and the amplitude of the flow variation as the valve hunts for position to control a stable flow and temperature. If we zoom into an operating hour during one of the tests, we can see that the off-coil air temperature is controlled much more tightly by the pressure independent control valve compared to the two-port modulating valve. Both the amplitude and frequency of the temperature variation around the set point is higher when a two-port modulating valve is used with an authority of 0.1 or less. We could see a similar situation occur with the relative flow control through the air handling unit when fitted with a pressure independent control valve or fitted with a two-port modulating valve. Again, the amplitude and frequency of the oscillations are higher when the air handling unit is fitted with a conventional two-port modulating valve. If we compare the relative cooling output of the air handling unit when fitted with a pressure independent control valve and two-port modulating valve, we can see once again the power output from the coil is much more stable when fitted with a pressure independent control valve. It is possible to use the pump affinity laws and the coil power output equation to compare the energy performance of the air handling unit when fitted with a pressure independent control valve and a conventional two-port modulating valve. In particular, we know that the change in pump power is proportional to the cube of the change in pump speed, and we know that the cooling power to be delivered by a coil equals the mass flow rate multiplied by the specific heat capacity of the fluid and the delta T of the supply and return water. The table shows the recorded average flow rates and water delta T's together with the calculated average pump power and daily cooling load delivered when air handling units are fitted with the pressure independent control valve and the two-port modulating valve. We can see that when averaged out, the same cooling load of 540 kilowatt hours is achieved at lower flow and higher delta T when the air handling unit is fitted with a pressure independent control valve. We can use our pump affinity laws to calculate the energy saving achieved due to the fitting of the pressure independent control valve. Finally, we can summarise our findings that when fitted with a pressure independent control valve, the same air handling unit can satisfy the same cooling load with 35% less pump energy consumption and an increased delta T. So from the results that we've collected in our test, we can demonstrate that an air handling unit, when fitted with a Frese OPTIMA pressure independent control valve, results in reduced pump energy consumption, increased water delta T across the chillers, the temperature control to the set point is tighter and more stable, the design of the valve ensures full authority of 1 at all flow settings, and a full modulating stroke at all flow settings. Of course, the valve is therefore easy to select with only the design flow and flange connection size necessary. It eradicates hunting, particularly at low flows, and these fewer movements of actuators result in a longer life expectancy of the actuator. So from our case study, we have been able to demonstrate a 35% pump energy saving, which results from more stable flow and a high authority on the control valve. However, we also saw an increased delta T back to the chiller plant, which will result in an improved coefficient of performance and a reduced energy cost into the chillers. Furthermore, when a variable speed pump, pressure independent control valve, remote sensors are used together, additional 70% of energy may be saved in accordance with the document BG12 energy efficient pumping systems. Thank you for listening, and I hope you found our presentation useful.